In today's lesson, we are looking at inverse variation and hyperbolas. Inverse variation is when two variables vary in opposite ways. This means that when one increases, the other decreases, and vice versa. Inverse variation can be written as the equation y equals k on x, where k is the constant of variation. When k is more than 0, the graph is decreasing, but when k is less than 0, the graph is increasing. So it's kind of the opposite to what you instinctively think. Inverse variation forms a graph of a hyperbola, so we actually need to look at all the different equations for a hyperbola. So obviously it has the equation y equals k on x. It also has the equation y equals k on bx plus c. It mentions there about the asymptotes. What the asymptotes are is that this curve will actually have lines where it will approach it, but it will never hit that line. So it'll never actually hit that line. And that's because of the way that the equation is written. The equation is always written with an unknown on the bottom, and when the unknown's on the bottom, we can't actually have it equals 0 on the bottom. So there's always going to be a point where mathematically it just can't exist. You can't have a fraction exist that has 0 on the bottom. So there's always going to be a part of the graph that just can't exist, and so that's what these asymptotes are. The asymptotes are basically where the equation cannot exist at all. So when we're looking at that, we're going to look at for y equals k on x, the x and the y-axis are always just going to be your asymptotes. So if you have a very simple one, then it's just going to be x and y are your asymptotes, nice and easy. When you have y equals k on bx plus c, the horizontal asymptote is still just the x-axis, but the vertical one is x equals minus c on b. Or you can solve this as an equation, which I do in the example which is coming up. Okay, so the first example is an inverse variation question. So we know that inverse variation can be modeled as a hyperbola, but this one we're just looking at trying to get the equation through inverse variation. So we know that the equation for inverse variation is y equals k on x. But for inverse variation problems, you always need to make sure that you put in the variables that you actually have. So for this one, I'm going to change it to n equals k on t. Alright, now to actually find k, we're going to use the information from the question above. So it says that in 12 hours, it takes 2 builders. So we sub that in. So the number of builders is 2. So we go through 2 equals k on 12 because it's 12 hours. So k will equal, well, it would just be 12 times 2, which is 24. So all I did there was times by 12 to get rid of that, and then times by 12 on that side too. Alright, once we have that, we just rewrite that equation up the top, but with k as 24 instead. So it just becomes n equals 24 over t. Alright, the second part is that we're going through and now we need to use that equation to solve a problem. So we have that we want to find out the number of builders needed for 9 hours. So we go through and it will be n equals 24 on 9. And that will equal 2.6 repeated. Now, of course, this is a practical kind of question. So you can't have 0.6 repeated of a person, so and would have to round up, so you would need 3 builders. Alright, going through and sketching the graph of y equals 1 on x. Basically, just to get the idea of what the shape should be, we're just going to do a table of values. 0 cannot exist. Now this is very important. This is the whole reason why we talk about the asymptotes. 0 cannot exist because you can't have a fraction with 0 on the bottom. Mathematically, it can't exist. So when we're going through, we need to make sure that we never have the denominator as 0. So that's where we actually get our asymptotes from. When we have this general form, we're always going to have x is 0 as an asymptote. but we can have other ones. You just have to make sure you're looking for where the denominator cannot equal 0. Alright, we keep going. We have 1, we have half, and we have 1 on 3. So if we actually graph that, we go through and we say, alright, let's say that that is 1 and 1. Then we go through and say, alright, that will be 2 across, but it's half. And then even lower again. And we're going to get this shape where it's kind of approaching, and the same thing there. It's approaching but never touches. And we'll have the same thing here too. So approaches but never touches. And lastly, domain and range. So domain's talking about the x values. So looking at our graph, we can actually see that the x values can repeat for infinity to the right, and also the x values can repeat for infinity to the left. So that means that we can go to minus infinity and infinity. We just can't touch the 0 in the middle. So we use what's called a union of domains. So we go through and we write for our left-hand side, we'll go minus infinity to 0, because we know we can't touch 0. But then we join it up, we use the union sign, so that just means you're joining it with something. And we go, alright, 0 for the right-hand side, and then to positive infinity. And that now means that we have a union of both of them, so that describes the whole domain for the thing. You're not going the left-hand side is that one, the right-hand side is that one. That's just saying the whole domain is that. So it can go off to infinity either way, but it just can't touch 0 in the middle. Same thing for the range. You can see that it's going to go up, and it's also going to go down forever. It just can't hit that middle 0. And we're done. So as I was saying before, when we're looking at the domain and range, we need to remember, especially for the domain, that that denominator can never equal 0. So when we're looking at domain straight away for this one, go through and say, for the domain, we know that x minus 3 can't equal 0. Now we solve this just like we do any other equation. So plus 3 to both sides. Therefore, x cannot equal 3. That will now give us our new asymptote. So looking at this, we know straight away that our new asymptote will not be the y-axis for the vertical one. This would actually be that at x equals 3, there'll be a vertical line that our curve will never touch. So we actually need to write up the domain though, so it will be minus infinity to 3, and then union of 3 to infinity. Alright, for the range, again, we're looking at it. If the denominator cannot equal 0, then the whole fraction cannot equal 0. And so that always means that our y value is just always going to be 0. The only time that's not going to be true is if it was an equation of 6 over y over x minus 3 plus something. That plus something would then mean, well, that can't equal 0, so then y cannot equal just that value by itself, just plus that c. So that would give you a new asymptote for the hyperbola. We don't have to worry about that. We don't have a plus anything, so we just know that y cannot equal 0. So then that means we have the same range as before. The last thing we need to look at is what type of shape the graph will make. So we say that as k is positive, which it is, 6 is a positive number. The graph means that is decreasing. So that means I draw it up. So I go through, I draw it up like that. I put my new vertical asymptote, which is 3. And so if it's decreasing, I know on this side, I'm going to have that it looks something like that. But what we are missing is that if I do that same curve underneath there, it is going to hit the y-axis somewhere. So I do actually need to calculate the y-intercept. So to find the y-intercept, we sub in x equals 0. So we go through and say, well, y equals 6 over 0 minus 3, which just becomes 6 divided by minus 3, which equals minus 2. So then we know that at the point minus 2 there, we are going to have an intercept. So we go through and now we can draw our graph. And just make sure that it hits through that point. Alright, going on to the next one, we need to graph this and we need to look at it in a similar way. So firstly, we need to look at, we don't actually need to define the domain and range for this. Because it's just asking us to sketch the graph, we kind of need to do some of the same working out that we did for the domain before, because we need to find if there is a new vertical asymptote. But we don't actually need to go through and state the domain and range formally like we did before. So going through, looking at the denominator, we know that can't equal 0, so we straight away go 2x plus 4 cannot equal 0. Again, like any other equation, so we go through minus 4, so 2x equals minus 4, cannot equal minus 4. And then divide by 2 on both sides. And we get that x cannot equal negative 2. So that will be our vertical asymptote. Looking through, same as we did before, for our horizontal asymptote, there is no plus anything over here. So we don't have to worry about there being a new vertical asymptote. Our vertical asymptote would just be 0. So we know we're going to have the x-axis as one asymptote, and then we're going to have the line x equals negative 2. X equals negative 2 as the other asymptote. So then we go through and we need to figure out what type of shape it's going to be. So looking at it, we actually have that you move the negative up the top. So that means that k is a negative number. So that means the graph is actually increasing. Last step that we have to do, because we could see from last time, we have moved the vertical asymptote, so we are going to have a y-intercept at some point. So we have to go through and find our y-intercept. So y equals negative 1 on 2 bracket 0 plus 4. So y equals negative a quarter, or 1 and 4. Alright, so again, drawing up. Remember with sketching, it doesn't need to be exact, you just need to have the right details on it. So going through, our new vertical asymptote will be x is negative 2, so it goes through there. Let's say negative 2 is there. Then we're good. Then we go through and we know that it is increasing, which means that you're going to have a line over here that doesn't really touch any of the y-axis. But then you're also going to have a line here that's increasing, and we know that it's going to hit at the point quarter, or negative a quarter. And now we just need to draw our line to make sure it actually hits there.